So hello everyone, and today we will be seeing one of the problem from Geeks for Geeks. It says Mother Vertex. So the problem goes like, given a directed graph with v vertices labeled from 0 to v minus 1 and a list of edges where each edge is represented as uv indicating a directed edge from vertex u to vertex v. Now we are required to find a mother vertex of a graph. So what is mother vertex? A mother vertex is a vertex from which all the other vertices can be reached. So if multiple such vertices exist, return one smallest value. If no such vertex exists, return -1. So cool. Well, nice. How are we going to approach? So first of all, what is mother vertex? Are we clear about that? So this is one of the example which indicates this graph over here. Now here there are, not to mention, 3 mother vertex, 0 to 1. How can you say so? So if I'm at node 2, I can reach every other node within the graph. So if I'm at 2, I can reach 2, 1, 0, 3 and 4. So likewise 1 is also mother vertex, 0 is also mother vertex, but 0 is the smallest mother vertex, so that is why the return is 0. Again, there is another graph. As you can see, there is no mother vertex over here. So if I'm at any of the node, I cannot 100% reach the other nodes. So if I'm at 1, I cannot reach any node. So if I'm at 2, I can just reach 2 and 1, 0, 0 and 1, that's it. So that's why there is no mother vertex, and that's why we return -1. Now things are clear, but how do we solve this? Let's understand the problem first. If I'm having this, okay, yeah. So within understanding the problem, first we would go first what is being asked. So they asked return mother vertex, and return the smallest if multiple, and return -1 if none. So there are 3 parts. First of all, let's see, do we understand mother vertex or not. So mother vertex, it has ability to reach every node. Great, this is awesome. Now it has ability to reach every node. So why cannot I do like, hey, I'm traveling one by one nodes from node 0 to node n, and within that I would take each node and understand that, hey, if this node reaches or not, rest of all, and if it yes, I will return that node, and yeah, that can work. But understand this point, this individual step takes you n iterations of nodes, and whether it reaches or not, it takes you again n iterations of node, and that's where your time complexity is not expected. So you see, the expected time complexity, they are asking v plus c, but we are going v square, which is a square of it. So obviously we will hit a time limit exceed. You can try this one, but again you will hit a time limit exceed, so bear with me. Is there any better solution? So again, let's understand where our solution failed. Our solution failed because of n cross n. We got an n square reach. What if I tell you that, hey, you don't reach to do n cross n? Because if you are reaching each and every node and you're performing a DFS operation in each of every node, you don't have to do that. So what I'm saying is, you're taking node 0 to n. You can do one thing, that, hey, you can check that, hey, if I have already visited the node, then why do I need to do a DFS again? So don't do a DFS over it. So that's where I say that, hey, if I have traversed within the node A, so this is a graph with vertices A, B, C, D. I'm not talking about any linkages right now, but if I'm visited A and A connects to C, and we also have E, F, we also have C, and C is connected to E. Okay, C is connected to F for a while. So when I'm iterating, I can iterate on B, but why should I iterate on C? Because I know C is already reachable. If I can say that, hey, if A is a mother vertex, why I need to reiterate on C? That's a good question, because I have already know that, hey, C is reachable by A. So why I'm trying to see whether what else I can reach on C, because I have already found out what else I can reach from C, which is F. That is why let's not do whatever we have visited. Let's take new. So new means which are unvisited. So every time we take new, how many times I can take new? There are n nodes, and every n node can be a new, because it's a disjoint graph. Maybe let's say it's a not disjoint graph, it is a proper disconnected graph. So that means it is n times I can go. So I already have a visited node, and I am sure that, hey, I'm visiting it only once. So only once visit. What do I mean by only once visit? I'll again re-clear. If I'm already have visited A node, is there any chance that I will go ahead and visit A node again once? No, not at all. If I have visited B, is there any chance? No, not at all, because I have kept a marking, and that's where I will write it also down. Keep a marking where you have visited and not, and keep track of last node which you have seen. Cool. Why I'm doing this, keeping a track. Let's come back to our solution, our scenario. So if A is connected to C, C is connected to F, and fortunately F is connected to all of these nodes. So F is connected to all of these nodes, that means B is also visited, D is also visited, and E is also visited. So problem solved. Next time if I'm running on to the node B and I see B is already visited, I'll not iterate. C is already visited, likewise I already visited, I will not iterate, and I will left with a last node which I have iterated upon. What was the last node I have iterated upon? It was A, and that is why I'll return A. But not always. What if F is connected to all of those nodes but not D, and my last node is D? So in that case, should I go ahead and return D? Obviously not, because D is not a mother vertex. So what I should do here is I should again check for the last candidate. So the last candidate, or the last node which we have picked, I just wanted to check it once, that, hey, I wanted to make sure that this is actually a mother vertex, and if it is a mother vertex, return true. Not true, but again node. And if not, I'll return -1. How are we going to keep track of a smallest multiple? Bear with me and we'll get to know. First of all, at least make sure that we are returning a mother vertex. So keep this for a while. So keep aside for a while. Cool. Now this is a very vague structure. We have edge list. I don't want to edge list. What I'll do here is I'll create a proper map of integer to set of integer, which is a map of hash map. Well, now for this edge within edges, what I'll do here is I'll check that, hey, map dot put if absent, because it might happen it is first time I'm seeing this edge of 0, new hash set, and map dot get edge of 0 dot add edge of 1. So don't get intimidated, this is just a conversion. This is a conversion from edge list to adjacency list. So our new graph resides within the map. Cool. Now let's go to back to our algorithm. Our algorithm, what it says go from 0 to n. Well, we will go from 0 to n then. So for int I is equal to 0, I is less than n, here is not n, here is v vertex, and I plus plus. Now next what it says, already visited, only visit once. So I don't know how to calculate visited, so what I'll do over here is to take a boolean, visited, vis for short, new boolean, how many vertex, v vertex, so v. So if visited of I don't want to visit it again, I'll continue to the next one, cool. Keep track of marking if you have visited and not. Okay, keep track of marking means I wanted to visit this one. Keep track of marking means I need to also send this visited. I need to send the graph because obviously graph is being iterated upon, and from where I'm going to iterate. So graph, a starting point, and a visited flags to keep track. And again, and keep track of a last node. We have seen last node candidate. So I'll say candidate is equal to -1 initially, and here I'll say candidate is equal to I. Cool. I think we have done over there, and ultimately what we are going to do here is check for the last node, last candidate again. So till this point we know that hey, this might work. I know I have to code DFS, but bear with me. So till this point we know that hey, I should possibly mark every visited node, and there can be a candidate which would actually be Mother Vertex, and this candidate should reach each node. And how do I make sure with that? So if I have an empty visited flags, that means new boolean of v, or for that matter I'll just say arrays.fill visited with false. So reset, I'm just doing a reset, and a candidate should reach each node. How can I ensure reaching the nodes? I'll just call DFS map and candidate and visited. And ultimately what I'll do over here is if I is equal to 0, I is less than n, or I'll just do a boolean x from visited, and if not x, then return false, not false, -1. It's something like if any of the entry I'm finding as false, then return -1. So that's where I confirm that it is not a Mother Vertex. But if this is not executed, then that means it is a Mother Vertex. I have took a doubt on it, so I'll return the candidate as it is. We are also here to make sure that this is the smallest, but before that I'll implement DFS. DFS is quite simple, as you know. It's void right now, and you don't have to return anything. What it takes, it takes map, which is our graph. Then what it takes is I and vis. I means source node, so int I, and visited is nothing but a boolean visited array. I'll just make sure that hey, if it's already visited of I, then return. I don't want it to recompute this one, and if it is not, I'll mark it as visited. True. Mark it, and once that is done, I'll check that hey, whether it has its own adjacent childs or not. How can I check that? Map.contains key. Or I'll just do one thing. I'll just say, anyways, I'll just check map.contains key, and I wanted to check what I. So if it has keys, then that's well and good. If it doesn't have a key, I'll just return, because it doesn't have any adjacent childs. So why should I go forward? And if it has adjacent child, let's take it one by one. Adjacent childs, which should be taken care by map.get I. Okay, so we have adjacent child. Now what? DFS onto that. So we have map, we have adjacent child. Let adjacent child move again in the depth with visited still intact. Now, coming back to our point, are we sure that we return the smallest multiple? And the answer is yes. Why so? Because we are iterating from 0 to v. Every index which we see is the smallest index. The starting index, if we found it, is the smallest index which we are storing within the candidate. If it is a mother vertex, we have iterated already all visited array, and the candidate variable would never get updated. Hear me again. If I have found the mother vertex at any position I, then this two lines would never ever execute, because this line would run and I will never pass on this, because I was a mother vertex, and never I will find any node which is unvisited. So everything is visited. So why should I again depth? So cool. Let's try to run this one. It runs for sample test cases. Let me try to submit this. And yeah, it got submitted for rest of all the test cases as well. So this was all about it. This had a topic tag of DFS, graph, data structure and algorithm. Pretty much everything we have seen so far is within the code. And for more such algorithms, graph trees, questions, click the video on your right, and I will see you in the next one.